All right, hi folks, this is Larry Muslino. I'm recording a video for MATH140. This is section 1.5 on the limit of a function. This PowerPoint file is posted in Canvas under modules. And this introduces the idea of the limit of a function. It can be very important because as we move forward in the course, we'll be talking about other concepts that rely on this intuition of a limit. So what is a limit? Well, let's do a quick example here to get a sense of what limits are all about. So let's say we have a function. Here it is, x squared minus x minus 2. I want to know what happens to this function when x takes on values near 2. What I might do is create a table. So notice here I created different x values. Starts out here at 1.0, 1.5, 1.8, goes all the way up to 1.999. Remember, I'm interested for x values near 2, so I'm going to let x be 1.999. Let me do it for values greater than 2. So here it is 3, 2.5, 2.2. Notice I'm getting closer and closer to the value 2. Here's 2.001. Let me look at the y value. What's happening to f of x? By the way, remember, f of x and y are really interchangeable. Sometimes we use y to indicate the value of a function. Other times we'll use f of x. Well, I can see here that the value of f of x, or the y value, is closer and closer to 2. Look, here it is 3.997. What's the value very close to 4? Over here, when x is 2.001, I'm seeing it's 4.003. So again, what I'm seeing here from this table, it seems to indicate that as x gets closer and closer to 2, y value seems to be getting closer and closer to 4. So that, in a nutshell, is what a limit is all about. As the x value gets closer and closer to some number, in this example was 2, what's happening to the y value? What is the y value getting closer and closer to? In this example, 4. Well, if we were to graph this function, we could come to the same conclusion. Now, let me just remind you that when you're graphing a function, any point on the graph is an xy point that satisfies the equation. So, for example, any xy location that I was to draw on this graph would be a corresponding solution to that equation. So imagine I'm going to move here on the x-axis, getting closer and closer to 2. So maybe I'll come closer to 2 from the left side. Also, I'll come closer to 2 from the right side. What's happening to the y value? Well, as x gets closer and closer to 2 from the left side, I'm really moving up this curve. Imagine a point that's moving up this curve. You can see as x gets closer and closer to 2, the y value is getting closer and closer to this y value, or this height of 4. The same would happen as if I was approaching 2 from the right-hand side. That means I would be coming down this curve, and again, the y value would be approaching 4. So I'm really seeing the same result graphically as we saw in that table on the previous slide. Let me clear these drawings off. Yep. All right, so that's what we say. We use this kind of terminology. The limit of the function as x approaches 2 is equal to 4. And again, what that really means is as x gets closer and closer to 2, we observe that the y value is getting closer and closer to 4. We call that the limit. So here's the way to think about this. As x gets closer and closer to a certain value, let's say a value c, sometimes you'll see x with an arrow. That means x approaching c. But here's a very important point. X gets closer and closer to c, but x does not equal c. So in that example we looked at a few minutes ago, x was getting closer and closer to 2, but we're not going to allow x to equal 2. That's very important. Then the corresponding y value gets closer and closer to some number. We're going to call that number L. In our example, the y value here was 4, right? As x got closer and closer to 2, the y value got closer and closer to 4. So the way we would write that is the limit. Let me write this here just to give you a quick example. The way we would write that example is the limit as x approached 2 of that function, f of x, the y value approached 4, So we would say equals 4. Okay, again, keep in mind what a limit is saying is as x gets closer and closer to some number, but does not equal that number, what is the corresponding y value getting closer and closer to? We call that the limit. All right, well, here's the fancy, let me go to the next slide. This is the fancy definition of a limit. Here it is in this box. It says when we write x approaches a, the limit as x approaches a of a function equals L, and you can think of it this way. If we let x get closer and closer to a, but not equal to a, then the values of f of x are going to get closer and closer to y. Okay? So let me go down here to this bottom. It says imagine x getting closer and closer to some number called a, and the limit means what is the values of y getting closer and closer to. That number L, we call it the limit. Keep in mind, x is not going to equal a. So again, we don't consider the scenario that x equals a. That can be confusing because sometimes you might look at a function and see that the function isn't defined at x equal a. Well, you don't really care that the function is not defined at x equals a because in the limit, we don't let x equal a. We just let x get closer and closer to a, but never get there. Let me try to illustrate that with a few graphs here. Let me try to go through this carefully to help us understand how limits are interpreted. All right, let me go to this leftmost limit. Excuse me, this leftmost graph. Well, if you look at the leftmost graph, this is similar to the example we did where the limit as x approached 2 was equal to 4. So if I look at this left-hand graph, I could say as x is getting closer and closer to this value a, it looks like the y value is getting closer and closer to this limit L, whatever L is. Remember in our example, we let a be 2, and this L value was 4. Let me go to the middle graph, because the middle graph is a little more interesting. What they're trying to show you here is there's a hole in the graph. It's a little hard to see. Let me actually see if I can zoom in a little bit on this to show you that there's a hole. Maybe now you can see that there's a hole in the graph. What this is trying to say to you is when you are thinking about limits, it really doesn't matter that the function is not defined as x equal a. Notice this function has this jump. So when you see an open circle like this, it means the function is not defined at this point L. This function, let me give you an example, we make L equal 4, and let me let this dot correspond to, let's say, a y value of 3. And I'm going to let this a be the number 2. And I asked you for this graph, what is f of 2? Well, when I go to this open circle here, what it's telling me is the function is not defined at that point. The function is defined by this blue dot. So f of 2 is really the y value of 3 here. What I could ask is what's the limit as x approaches 2? Well, what I'm asking is what happens as x gets closer and closer to 2 but never gets there? The fact that there's a jump in this value of f of x really doesn't matter to me because I'm not going to let x equal 2. I'm just going to let x equal get closer and closer to 2. So in this example, as x gets closer and closer to 2, the y value is still getting closer and closer to 4. So we would say for this example, the limit as x approaches 2 is the value 4. So in this middle graph, f of 2 is defined. It happens to be the value 3, but notice that plays no role in determining what the limit is. Because again, the limit does not involve x equal to. It only involves x getting closer and closer to. All right, let me go over to the rightmost graph. The rightmost graph is trying to show you that there's a hole, but there's no corresponding value for x equal 2. So if I said to you, what is f of 2? The answer is there is no value. We say DNE. DNE means does not exist. Because there's a hole here in this function, and there's no corresponding y value, then we say f of 2 is DNE. But let's do the same limit question. What's the limit as x approaches 2 here? Does it matter that the function is not defined at x equal 2? No, it doesn't matter, because for the limit, x is approaching 2, but not equal to 2. So again, we would say the limit as x approaches 2 of this function would be 4. I'm assuming that this L value is 4. Okay, so the important part of this slide is to recognize that it really doesn't matter if the function is defined at x equals a certain number when evaluating a limit, because remember, the limit only depends on getting closer and closer to that x value, but don't let x equal that particular x value. We'll do some examples, by the way, in a few minutes. All right, let's take a look at this example. So you're trying to come up with the value of the limit as x approaches 1 of this function. Now you might notice I can't actually let x equal 1, because if I let x equal 1, the denominator would be 0. Right? Because I would have 1 squared minus 1 in the denominator. That would be 1 minus 1. That would be 0 in the denominator. But of course, you remember you're not allowed to divide by 0. So I can't let x equal 1, but that doesn't really matter to me. When I take the limit, I'm only letting x get closer and closer to 1. I'm not letting x equal 1 itself. Well, let me come up with a little table here to help me out. So I'm going to take this function, and I'm going to come up with values closer and closer to 1. So you can see I'm using 0.9, 0.99, 0.9999, and so on. When I approach from the other side, I'm going to go with 1.01, 1.001, and so on. Look what's happening to the y values as the x values get closer and closer to 1. It looks like the y value is getting closer and closer to 0.5. And so we say the limit of that function as x approaches 1 is equal to 0.5. It doesn't matter. The function is not defined at x equal 1, because we're only interested in x approaching 1. Here's another similar example. What this example is doing is it's a new function. It's a brand new function. It says this function g of x is going to be equal to the blue curve, except when x equals 1, the value of the function is 2. You might remember this is called a piecewise function. What it says is when x equals 1, the y value is going to be 2, but when x is anything other than 1, the y value is given by this fraction. Well, if you were to graph this, you'll notice that there's a hole in the function at x equal 1, but here's the value y equal 2, so there's a jump. But again, this doesn't matter to me, because as x approaches 1, you can see the y value is approaching 0.5. It doesn't matter to me that there's this jump in the function at x equal 1, because I'm only allowing the function to get closer and closer to 1. All right, well, in the examples we were just looking at, we were kind of looking at what happens as you approach x from the left or from the right. But we can also approach just from one side. Let's say I just wanted to approach its value from the left or the right side. We call this one-sided limits. And here's the notation we use. When you see the limit as x approaches a, with a minus sign as that superscript, that's really telling you that you're approaching from the left side only. So this example would say the limit as x is approaching a from the left side of this function. So if you think about this graphically, you would only be coming in from left to right only as you approach that x value. Let's take a look at an example. do an example in a second. Here's the fact that we could have a left-sided limit, or we could approach the x value from the right side. For that, we're going to use the notation x approaches a with a plus sign as a superscript. It's called the right-sided limit. Now, what this theorem is trying to say here is the limit as x approaches a is equal to L if and only if the left-sided limit and the right-sided limit are equal to the same value. Let me say that again. The limit as x approaches a is equal to L only if the left-sided limit is the same as the right-sided limit. If the left and right-sided limits don't agree, if they're not equal to each other, then we're going to say the limit does not exist. Let me give you some examples to help illustrate this. All right, let's do a couple of these examples. I'm on slide 16. All right, part A says, what's the limit as x approaches 2 from the left side? All right, let's try to work through these carefully. So I'm doing part A here. Part A says I'm going to approach x coming into the left side. So let me ask myself what's happening to the y value as x approaches 2 coming in from the left side. Well, if x approaches 2, I'm going to be on this blue curve here, and you might notice as I'm getting closer and closer to 2, I'm drawing in these red dots. You might notice the y value is getting closer and closer to 3. So the answer to part A is a y value of 3. All right, let me go to part B of this. Part B says, what about the limit as x approaches 2 from the right side? Well, if I'm coming from the right side, then I'm moving down this curve. I'm going to draw some blue dots to illustrate moving down this curve. See, the y value is getting closer and closer to 1. So this answer is equal to 1. Now notice what just happened. The left-sided limit was 3. The right-sided limit was 1. Because those two results are not equal to each other, when it comes time to saying what's the limit as x approaches 2, we would have to say D and E does not exist. The only way the limit exists is if the left-sided limit and the right-sided limit were equal to the same number. But in this example, they're not. So we say D and E. By the way, when you see the limit as x approaches 2, you can almost think of this as a two-sided limit. It really means you're approaching from both the left and right side. All right, let's do the bottom example. Let's go to part D. Part D says, what about the limit as x approaches 5 from the left side? All right, let me approach 5 from the left side. Well, if I approach 5 from the left side, let me draw some red dots on the graph. It looks like the y value is getting closer and closer to 2. So this limit looks to be 2. Does it matter that there's a hole at x equal 5 and then a jump in the function? Because if you ask the question, what is f of 5? Well, f of 5 would correspond to that solid dot. It looks like f of 5 is equal to 1. But remember, I don't really care what happens when x equals 5. I'm just getting closer and closer to x equal 5 coming in from the left side. All right, let me come in from the right side. So let's do part E. What about the limit as x approaches 5 coming in from the right side? Let me draw some blue dots to move along the curve as I'm getting closer and closer to 5 coming in from the right side. Well, you might notice we're going to end up with a y value of 2 again. And now the left-sided limit and the right-sided limit are equal to the same value, namely 2. So when it comes to this two-sided limit in part F, the answer is 2. Okay, so notice the left side and the right-sided limit have to agree or have to be equal to the same number for the two-sided limit to exist. If the left-sided limit and right-sided limit do not agree, then the limit Okay, so folks, let me go here to slide 19. Here are two important concepts. As we mentioned earlier, when you take the limit of a function as x approaches as x approaches c here, it doesn't depend on the value at x equals c. You're only getting closer and closer to the number c, but you're not letting x equal. Also, for a limit to exist, you must come up with the same y value, the same limit, if you approach from the left side as if you approach from the right. If you don't come up with the same limit answer, then the limit doesn't exist. All right, let's go to a WebAssign example. This is a homework problem you'll be working on. And they're giving me a graph. And the first question they're asking me here in part A is, what's the limit as x approaches 2 coming in from the negative side? All right, so on the x-axis, let me approach coming in from 2, coming in from the left side. So I'm getting closer and closer to 2. What's the y value doing? Well, let me draw some blue dots on the curve as x approaches 2 from the left side. Well, I'm noticing the y value is getting closer and closer to 3. This is not labeled here, but this horizontal line is y equal 3. So you can see the answer to part A then is 3. All right, let me go to part B. Part B says, what's the limit of this function as x approaches 2 from the positive side? All right, so let me come in approaching 2 from the positive side. And again, let me draw some red dots on the graph. As x approaches 2 coming in from the right side, I'm moving down this downhill portion of the graph. You can see that the y value looks like it's getting closer and closer. And then part C says, what's the two-sided limit? Well, because the left-sided limit and the right-sided limit are not equal to each other, remember for the left-sided limit, I ended up with the answer 3. The right-sided limit, I ended up with the answer 1. Because those two results aren't the same, then the answer for the two-sided limit is D and E does not exist. Okay? All right, folks, well, let's expand this a little bit to consider the case. What happens if the y value approaches infinity as x approaches a certain number? Let me show you some examples of that. So what could happen is, as x approaches a certain number, the y value could get larger and larger, and when that happens, if it gets arbitrarily large, we say the limit is equal to infinity. Okay? So again, the translation here, imagine x getting closer and closer to some number called a. Remember, you never let x equal a. The y value might get larger and larger, and then we say the limit is equal to infinity. Okay? Let's take a look at an example. And let me, to make this a little more concrete, use, let's say, this is x equal 2. And I ask you, what's the limit as x equals 2, as x approaches 2 for this function? I'm going to approach 2 from the left side and the right side. Well, as I come in and approach 2 from the left side, let me draw some red dots on the graph so see what's happening to the y value. Notice the y value is larger and larger, and you can see the y value is heading up. Let me approach x equal 2 from the right side. Well, if I come in from the right side, let me draw some blue dots on the graph. Again, I can see the y value is getting larger and larger. So the answer here would say this limit is equal to infinity. All right, let me go to the next slide. It could also turn out that the y value gets smaller and smaller. So instead of the graph heading uphill, the graph might head downhill, like this slide. And of course, the same scenario, but now the y value is heading to negative infinity. So again, as x approaches a, you can see the graph is heading the y values are getting smaller and smaller. You might say they're getting larger in the negative direction. And we would say the limit here is negative. Okay. So again, if x is getting closer and closer to some number, call it a, the y value might get smaller and smaller, and so we say the limit is equal to negative infinity. Okay, and you can have the same kind of one-sided approach. These examples, you'll notice the graph is approaching infinity from either a left side or right side example. All right, let's go to WebAssign. We'll do an example here from WebAssign. This is a homework problem. All right, let's go to part A here. Part A says, what's the limit as x approaches 2 for this function? All right, well, let me approach 2 from the right side and also from the left side. Well, in either case, I'm noticing the graph is heading down, down, down. Right, the y values are getting smaller and smaller. So it makes sense here. The answer should be negative. Let's go to part B. It says, what's the limit as x approaches 5 for this function? All right, so let me go ahead and approach x equals 5. You might notice what happens. X approaches 5. Well, the graph is heading uphill. I'll draw some red dots on the graph. You can see the y value is getting larger and larger. And you can see the y value is heading to positive. All right, let's go to part C. Now, part C is a little tricky. It's a one-sided limit. It says, what's the limit as x approaches negative 3 from the left side? So let me go ahead and approach negative 3 coming from the left side. Let me put some dots on the graph to show what's happening to the y value. See, the y values are getting smaller and smaller. So this left-sided limit ends up being negative infinity. Okay, let's do a couple more examples. Let's go here to a WebAssign example. And this one says use a table of values to estimate the value of the limit. And if you want to use a graphing calculator of some kind, you can confirm your result graphically. So it says, what's the limit as x approaches 0 of tan 7x over tan 4x? All right, well, if you were to graph this, you might be able to see what's happening, but also, what if we just use a calculator to help out? So imagine if x approaches 0, remember what that means? That means x is closer and closer to 0, but never actually equals 0. So how about if I let x equal a value very close to 0 from the left side? Maybe I'll try negative 0.01. Or I could even try x equals negative 0.0001. Right, I'm just picking arbitrarily small values of x close to 0. Well, I could plug this into my calculator and see what happens for the y value. I could also let x be a very small positive number. So I could let x be, let's say, positive 0.001. Again, I'm just picking a value arbitrarily close to 0. Well, if you plug this in your calculator, you would take tan of 7 times that x value divided by tan of 4 times that x value. You'll see that your answer will be a number very, very close to 1.75. So remember, by the way, folks, on the homeworks, you can use a calculator for assistance when you go to take exams. Calculators are used, so this type of question will not show up on any of the exams or show up on the final. All right, folks, let's do one more slide with some more WebAssign examples. Let me go here to slide 30. All right, so these are asking you to decide what happens for these limits. All right, let's go to the first example here. It says, what's the limit as x approaches -7 from the plus side? All right, well, let me think about this for a second. Let me draw a number line just to help me out. Let's say this is the x-axis, and here's -7, and they're asking me to approach -7 from the positive side. So that means coming this way. So what's a value very close to -7? Well, maybe I can pick a value like -6.99. That's a value very close to -7 coming in from this right side. Well, let me try to analyze what's going to happen. If I were to plug in -6.99 into this fraction, I would end up on the top of this fraction. Remember, x is going to be -6.99. Top of the fraction would be some positive number. And the bottom of the fraction would also be a positive number. Right? The bottom of the fraction would be -6.99 plus 7, but that's 0.01. So I'm going to end up with a positive fraction out of this. The denominator is going to be a number very, very close to 0. You can imagine if you let x be -6.9999. Well, what happens to a fraction if you divide by a very, very small number? Imagine the denominator was 0.00001. Well, if you have a fraction divided by a very, very small number, the fraction itself is very, very large. So does it make sense the answer here can be positive infinity? By just picking a test value like -6.99, told me that both the numerator and denominator were going to be positive values. So I know this fraction is going to be positive. I also know the denominator is going to be very, very, very small as x gets closer and closer to -7 coming in from the right side. And that tells me I'll have a very, very large fraction, which corresponds to the answer positive. All right, let's go to number 9. Again, I'm going to draw a little x-axis here to help me out. So here's -4, but now they're asking me to come in from the left side. Right, this is a left-sided limit. So I'm going to be coming in from this side, and let me just pick a test value. Well, if I'm coming in from the left side, how about if I pick -4.01 coming in from the left side? All right, let me analyze what happens if I let x equal -4.01. Well, the numerator of this fraction would be positive because it would be -4.01 plus 5. That's positive. But notice the denominator would be negative, let me do it over here, -4.01 plus 4. But notice that's going to be a negative result, right? This will be -0.01. So that means the denominator is going to be negative. Well, a positive divided by a negative I know is negative, so this fraction is going to be negative. Also, I know the denominator is going to be very, very small. And again, if I divide by a very, very small number, the fraction itself is very, very large. But the fraction is negative. So it makes sense here the answer should be -infinity for this limit. Again, if you want to graph these functions, that would be a good idea to get a visual picture of what's happening. All right, the very last problem, it says what happens when x equals -2, when x approaches 2, when x approaches 2 coming in from the left side. Let me draw a little number line here. Here's 2, and they want me to approach from the left side. So maybe I can use a test point, say 1.99. Now I could plug 1.99 into this function and see what happens. I'm noticing I can do a little simplifying. Because the top I could factor as x times x minus 2. And you might notice the denominator is x minus 2 times x minus 2. I'm just factoring top and bottom. But when I do that, x minus 2 cancels out. So now this will help me, this will make the analysis a little easier. Now let me let x equal 1.99 in this fraction. Well, if I let x equal 1.99, the top of the fraction is going to be positive. But notice the bottom of the fraction is going to be negative. Right? Because if we take x minus 2, x equal 1.99, that will end up being 1.99 minus 2. That's a negative number, right? Negative 0.01. So this is similar to the previous example. We're going to end up with a negative number on the bottom. It's going to be a very, very small number. So it makes sense the answer here should be negative infinity. Okay, folks, hope this helps get you started in the section 1.5. This is introduction